only 350 is the alveolar ventilation reaching the alveoli. Now the rest of it remains in the dead space called the anatomical dead space, the conducting airways which are not taking part in gaseous exchange. So an estimate of this, the guesswork is that 1 ml of dead space is present per pound of body weight. That is, approximately the value ranges from 130 to 180 ml. But we cannot always work on guesswork or the calculated estimates like this. What we need to know is the exact anatomical dead space. In principle, you can say how it can be done. So on the right, this is a diagram showing 3 pictures. In the first one, there is a test gas which is present in the balloon, about 500 ml of that. So the person inspires, and as a result of that, this 500 ml of the test gas, which is shown there as dark dots in the concentration present in the balloon, it enters the whole respiratory pathway up till the alveoli, so that when it reaches the gas exchange area in the alveoli, it mixes with the gas which is already present and it gets diluted. That's why you see the different shades of dots, that is, it is diluted in both the lungs as compared to that which is present in the conducting airways, which is shown as the same as in picture A. So this concentration going up to the conducting airways, at the end of the conducting airways, up to that is still the same which was present in balloon, because it has not mixed or is not taking part in gas exchange, whereas the rest gets diluted in the alveolar spaces or lungs. So then the person expires the test gas out. So as it expires, first air which is present in the conducting airways, the more concentrated one, will go back into the balloon, and the rest which is coming out is from the alveoli later. So as a result, the initial part is the concentrated gas, and then it will be the diluted, and at the end of the expiration, what comes out and is present in the balloon is a mixture of what it was earlier, which is coming from the conducting airways, and a part from the alveoli which is diluted. So it will be somewhere in between, whereas the conducting airways now will have the diluted test gas which is coming up from the alveoli and stays there. So this is what is written here in the slide on the left hand side, whatever I have said, that the final test gas is now a mixture of undiluted from the dead space and the diluted alveolar space. So that's how the changes occur, how the gas is moving. The upper diagram, similar to that, shows a tidal volume of 150 ml, in which the purple thing is the alveolar ventilation and 150 ml above is the anatomical dead space. So this one is to go in with each inspiration, the total volume. How it will go in? It will, on the diagram on the left, shows an alveoli, and the conducting airways have a yellow colored air column which is shown in yellow, which is alveolar air from the previous breath. So this was the one in the conducting airways. Now when you inspire, this alveolar air from the previous breath, what was left in the conducting airways, first goes into the alveoli. This is then followed by part of the inspired gas from the tidal volume, and the one which remains above is the dead space air, that is 150 ml. So what we have is the alveolar air from the previous breath which is left here, plus the inspired air that participates in gas exchange. So the concept which is to be taken in, that there is some amount of alveolar air, not some, 2 to 3 liters, and that gets diluted by the fresh air what we take in, and there is some amount of the fresh air which remains in the conducting airways, and this principle will be used for the estimation of the anatomical dead space. In the next few slides we will see. So now that we know that out of 500 ml we have 150 ml as the dead space, then how does it affect the alveolar ventilation and the minute ventilation when it changes? How does it affect our total ventilation there? That is, supposing the breathing pattern is changed to slow and deep, so that the tidal volume now becomes 100 ml and the person is taking 6 breaths per minute. As a result of that, the total minute volume ventilation, that is, it is 1000 into 6, that is 6000 is the resting minute ventilation, and out of this the total dead air ventilation which remains in the dead space is 150 multiplied by 6 is 900, and the rest remaining, that is 6000 minus 900 is 5100 going to alveoli for gas exchange. Whereas if it was a normal 500 ml tidal volume breath with 12 breaths, more number of breaths, still the volume which is coming to alveoli is 4200. So when you increase the depth, alveolar ventilation is increasing. If you decrease the breath but increase the breathing frequency, so that the resting minute volume is same, that is minute ventilation remains the same in all of three, but here because it is the fast and shallow breathing, that is 40 into of this 150 ml, supposing we take the tidal volume, the whole will remain only in the dead space. So as a result, none will reach the alveoli. This is just a hypothetical situation. It can, you can have a situation like this very few times, but otherwise if it is more than 150, say 180, only 30 will go to alveoli per minute, so that some fresh air is mixing. So whenever the depth of the breathing is changed, the tidal volume is changed, although the minute ventilation remains the same, the amount of alveolar ventilation changes. So that is what was given in the last slide and is given now here also. So anatomical dead space is the dead space or the volume of air remaining in the conducting airways. Why it is called? Because it is in the anatomical pathways and can be seen. Whereas the physiological dead space is the functional dead space. This is the dead space which includes not only the conducting airways, which are up till 16th generation, but also some part of the alveoli which are not receiving any blood flow. So if they are not perfused, air is just entering and they remain a part of dead space of the system. So this is also called alveolar dead space, that is unperfused alveoli. So alveolar dead space plus conducting dead space or anatomical dead space is called the physiological dead space. In a healthy individual, these two dead spaces should be equal. But if there is some alveolar dead space, then the physiological dead space becomes more than anatomical. So how do we find out the anatomical and physiological is to be seen. So this is a method which is shown here. It is called the Fowler's method. This is showing how we can find out the anatomical dead space. This is by taking a single breath of 100% oxygen. So this why it is called single breath nitrogen. By after a single breath we measure the nitrogen in the expired air. So the person is asked to take an inspiration of 100% oxygen. So now when he is taking inspiration, he is having only oxygen coming in because 100% oxygen. No nitrogen is coming in. So whatever was there in the conducting airways goes in first into the alveoli, and which already have 80% nitrogen in the alveoli initially. So after taking a deep breath, we ask the subject to hold for 1 second and then ask to exhale, and then you collect the exhaled air separately to know the volume also, and monitor the concentration of the nitrogen at the mouth to know how the nitrogen is changing as the person is expiring it out. So I think you can guess that as the person expires out, the first air which will come out will be from the conducting airways. This is the air which is left at the end in the conducting airways after taking 100% oxygen. So in the dead space it is only the 100% oxygen. It will not have any mixing from the alveoli. So initially the nitrogen concentration when you measure will be 0. So it will have 0 nitrogen as measured. Then as there is mixture, more and more alveolar air is starting coming and mixing and coming out, the nitrogen starts increasing, and then finally it reaches an alveolar plateau. So initially it is only conducting, then there is a mixture with some from the conducting airways, some from the alveolar, then there is finally more of the alveolar and less of conducting, and finally a plateau where it is exactly coming from the alveoli. So we can measure the volume of air which is coming out when the alveolar plateau is there and when this initial part of nitrogen concentration is there. This is the point which is taken between at the rising phase of the nitrogen, the mid portion where the two areas shown in blue, that is they are equal, that midpoint, that is taken as the end of the conducting airways, and that point, at this point, whatever was the volume is taken as the volume of dead space. So this is the measuring only the anatomical dead space, which should be in health equal to physiological dead space. But if there are certain alveoli which are ventilated and not perfused, they will be leading on to alveolar dead space. So how do we measure? We can measure it using the principle that whatever carbon dioxide is coming from our body from in the expired air is coming only from alveoli, from our body metabolism. So conducting airways do not have any carbon dioxide because they are not taking part in gaseous exchange. So and another thing which you need to remember is that the arterial CO2, that is the arterial carbon dioxide, is almost equal. It is always equal to alveolar CO2 in health. So these are the two things, and the second, there is a conservation of mass, that is whatever amount is taken in the tidal volume is equal to anatomical dead space plus the alveolar ventilation, and that's how we will use for carbon dioxide to derive the total physiological dead space. So I will just read it for you so that I have not missed it. CO2 can be added to the expired gas, as I said, only from those alveoli which are perfused and ventilated, because only when the gaseous exchange occurs, CO2 is entering the alveoli, and CO2 in the inspired air is very small. So only if those alveoli which are not having any perfusion, they will not have much CO2. They will not have any CO2 because it is from only the inspired air. So whatever CO2 comes in the expired air has come from ventilated and perfused alveoli. So now consider the equation, that is the total amount of carbon dioxide in expired air which can be estimated is equal to the carbon dioxide in the dead space ventilation and alveolar ventilation. But we know that the dead space there is no CO2, so whatever is coming in the expired air is coming from alveolar. So the Bohr dead space equation is Vd by Vt, Vd means the dead space volume, divided by the total volume is equal to alveolar partial pressure of carbon dioxide minus expired air partial pressure of CO2 divided by the alveolar partial pressure of CO2. So this is the Bohr's dead space equation, and we can find out the Vd. This can be found out because we can know the tidal volume, you know the expired CO2, and to know the PA CO2, we have written above that arterial CO2, we have taken this assumption that PA CO2 will be the same as arterial. So you can measure the arterial CO2 and derive at the value of Vd by Vt or the dead space. So it is based on carbon dioxide estimation from the alveolar air. So how did we come to that equation which was written in the last slide? The total amount of expired CO2 that is coming from the tidal volume, that is in the whole expired CO2, it is tidal volume multiplied by the fraction of expired CO2. It will be equal to alveolar volume and fraction of alveolar CO2. What is missing in this particular step is plus dead space volume and its CO2 concentration, because that's inspired CO2 concentration is considered to be 0. So that part disappears from the equation. So we have now two situations, that tidal volume into FeCO2 is equal to, that is alveolar volume multiplied by the fraction of the alveolar CO2. So changing, it is difficult, you cannot measure the alveolar volume like this. So you can change it to alveolar volume, we know, or the alveolar ventilation is tidal volume minus dead space. So you can just replace it or substitute it with it, so that now you have the equation as written in step 2. In the step 3 we rearrange it so that the tidal volume components come on one side and the dead space volume remains on the other. Also the fraction of CO2 in the alveolar air and the expired air, the partial pressures are directly proportional to it, or partial pressure of CO2 is equal to the fractional concentration measured by the barometric pressure, as we have done earlier. So you can change these values, replace it with the pressure values rather than having the fractional concentration. So this is the final equation, which was the Bohr's equation, which was given in the last slide. So what we are doing actually are asking the person to inspire and then expire, and then in the expired air we are measuring CO2, and based on assumption that whatever CO2 comes out from the body, from the alveoli, and alveolar and arterial CO2 are equal. So these are the assumptions. Based on that we can measure the physiological dead space, and we know the anatomical dead space. If there is any difference between the two, it is due to alveolar dead space. Then we have talked about that in the alveoli we have oxygen, which is 104 millimeter of mercury, and PCO2, which is 40. So with each breath, stop reading first, just listen to me. So with each breath, when we take in air, the partial pressure of carbon dioxide will decrease because CO2 is coming out with expiration, and in the alveolar air it will decrease. Whereas in the alveolar air, the amount of carbon dioxide which is there gets increased as the body produces more by metabolism. So there are 2 points to be remembered, that the amount of carbon dioxide in the alveoli is a balance between the two. It is dependent upon the amount of CO2 produced in the body and is inversely proportional to its removal by the alveolar ventilation. So more is the alveolar ventilation, less will be the alveolar level of CO2. More will be the body production, more will be the alveolar level of CO2. So this relation can be given in this equation, that is the alveolar ventilation equation, where alveolar partial pressure of CO2 is directly proportional to the VCO2, that is the amount produced in the body by metabolism, which is to be excreted, and inversely proportional to alveolar ventilation, because with each alveolar ventilation it is being washed out and the levels in alveolar decrease. We can rearrange this to show that alveolar ventilation can be given as VCO2 divided by PaCO2. So this is the diagram taken, I think the same diagram is there in Guyton also. This shows the relation that as the amount which is metabolized or is to be excreted increased, there is a change in the alveolar ventilation. This shows the effect of alveolar ventilation. The red line shows the effect of alveolar ventilation at a normal level of CO2 production. What changes occur in the partial pressure of carbon dioxide? A is the operating point, that at 200 ml of CO2 being produced or to be excreted per minute, the alveolar ventilation of 4.2 liter per minute is there to bring about an alveolar partial pressure of 40 millimeter of mercury. If it is, that amount to be excreted is increased 4 times, then the alveolar partial pressure to be maintained at 104, we require the alveolar ventilation to be increased from 4.2 to 16 point something or 17 point something, so 4 times. So as to maintain the same level of alveolar PCO2, 40 millimeter of mercury, not 104. So maintaining the same level of 40 millimeter of mercury of PCO2, we need to increase the alveolar ventilation 4 times, so that the amount which is excreted, which is 4 times, can be removed and the same level of alveolar PCO2 can be maintained. I think by mistake I said 104, that is for oxygen, just by mistake I said it. So this is just a diagram showing the relation between carbon dioxide partial pressure in the alveoli with the alveolar ventilation and amount of CO2 produced. What happens with the changes in the PO2, that is how the alveolar partial pressure of oxygen will change with the change in the alveolar ventilation. With the alveolar ventilation, this is you can just imagine, that is, you are taking in air. So by logic, whenever you are taking in air, we know the concentration of oxygen in inspired air. So depending upon that, our alveolar PO2 would be affected by the concentration of oxygen in the inspired air. Then how much is the alveolar ventilation, how much is the dead space, and how much is the alveolar. If we are taking deep breath, more amount of alveolar ventilation or fresh air will reach it, and how much is being exchanged with the body, how much is being removed by the pulmonary capillaries in the lung. So its entry into the alveoli from above and its removal into the pulmonary capillaries from the lung, the balance between the two would determine how much is the PO2 in the alveoli and how it can be manipulated. So the amount of oxygen, that is, if you see the diagram here on the right, again similar diagram to the one for carbon dioxide, that is, we have alveolar ventilation on the x-axis, and on the y-axis we have alveolar partial pressure of oxygen. There is an upper limit of maximum ventilation. Why it is written? Because this alveolar partial pressure can be reached up to a maximum of the partial pressure which is there in the inspired air, which is coming from the barometric pressure outside. That is, whatever is coming in the inspired air, supposing 149 or 150 millimeter of mercury, we can have the alveolar pressure maximum up till that, not beyond that. So the red line is the normal line which shows that what are the changes occurring in the alveolar partial pressure of oxygen with changes in alveolar ventilation. That is at 4.2, which is the normal level, which was shown for carbon dioxide curve also. The partial pressure of oxygen is 104 millimeter of mercury when 250 ml of oxygen per minute is taken in. Whereas if it is changed, that is, if the intake is to be changed, or that to 800, or here it is 1000 it is written. So if instead of 250 ml per minute, the uptake of oxygen as in exercise or some other reason it is increased to 1000 ml of oxygen per minute, So to maintain the same level of the alveolar PO2, which is 104, the alveolar ventilation needs to be increased. But it does not have the same relation as in carbon dioxide, which stated that if you double the alveolar ventilation, the changes in partial pressure of carbon dioxide were becoming half. So here when you increase the alveolar ventilation, double it, that does not mean that the alveolar oxygen will become double, because it can go up to a maximum of 150 millimeter of mercury and not beyond that. So it is not a direct relation as it was there. The relation which is given is that the amount of the partial pressure of oxygen in the alveolar air is maximum it can reach is the inspired partial pressure. But if it reaches 149, that means there is no alveolar CO2. Normally we are saying that alveolar CO2 is partial pressure is about 40 millimeter of mercury, and in a normal subject it goes up and down by 2 to 4 millimeter of mercury. So the maximum that is the alveolar PO2 is given by this equation, that is inspired PO2 partial pressure, inspired partial pressure of oxygen, that is partial pressure in the inspired air, minus the alveolar pressure of carbon dioxide divided by R, which is respiratory exchange ratio. This is the alveolar gas equation, which is given in the next diagram, next slide also. So the total amount of oxygen which can be taken in, or which is taken in, is inspired oxygen which you were inspiring, and then what you were expiring from the actually the alveolar air, what you are expiring from the alveoli, that is the air which is oxygen which is coming out from the alveoli. So inspired minus the alveolar which is going out, the difference between the two levels will give you the oxygen uptake. When the RQ is 0.8, more amount of oxygen is used, that is 250 ml, as compared to carbon dioxide which is 250 ml. So these two values Vi and Va what are written in the equation, there is a slight difference in that. But if we presume that these two are equal, 250 and 200 here, that is the volume is considered to be equal, then you can exchange Vi with Va and you can derive this equation what is written on the right, that is if Vi is same, that is inspired volume is same as the alveolar for the oxygen, then you will have this relation, that is Va into FiO2 minus Va into fractional, and the fractional concentrations as I said are directly proportional to Pi, that is the partial pressure. That partial pressure of a gas is directly proportional to the fractional concentration. So we replace them with the partial pressure values, and as a result finally we derive at the alveolar gas equation. Now if you remember this particular step, that is VO2 is equal to Va into PiO2, this is the equation B which is written here from the last slide, and the equation A we have taken from the carbon dioxide partial pressure, which is in the alveoli is directly proportional or is equal to the amount to be excreted divided by alveolar ventilation. So these are the two equations which are used to derive alveolar gas equation. So by these, if we substitute the values of VCO2 divided by VO2 is R, which is equal to this, finally we come out to this value. Like in VCO2, instead of VCO2 you can put these values which are given in equation B. So finally as a result we will come to this equation what was shown for the oxygen, that is alveolar partial pressure of oxygen is equal to inspired partial pressure of oxygen. It can come closer to it if minus the alveolar carbon dioxide depending upon the R, which is respiratory exchange ratio. So if we know the R and we know the inspired PO2, then we can relate the changes occurring in the alveolar oxygen and alveolar carbon dioxide. So this is what I have told you, the main points today in the class, that is ventilation of the lungs depends upon the frequency and depth. Minute ventilation is 6 liter, of which dead space ventilation is approximately 1800, the rest goes alveolar ventilation. The dead space ventilation, the main role is removal of the foreign particles and conditioning of the inhaled air. So it is not that why waste 150 ml, it is not being wasted, it is preparing the air for the gaseous exchange. So alveolar dead space will include only those alveoli which are not perfused, which are present in various disease or conditions or pathologies, and the total physiological dead space or functional dead space is alveolar plus anatomical. And regarding the CO2, what we said, that alveolar ventilation is minute ventilation minus dead space and is determined by the ratio of the CO2 production to the alveolar ventilation. The last point, alveolar and arterial CO2 tensions are very similar to each other, and it is strictly regulated to maintain changes in pH. Now, an important question which comes is, find out in physiology, we may ask the Fowler's dead space, but we can ask the physiological dead space, and there is a practical also in physiology to determine the physiological dead space. So we use that equation, the Bohr's equation, where we presume that all CO2 comes from the alveoli. So based on that, we will derive the physiological dead space by knowing the volumes also. So this is in brief. Now what we have not talked about in the alveolar ventilation part here for today is how the changes are occurring in the different regions of the lung in the alveolar ventilation. That we will be talking in the class on ventilation perfusion ratio. But I must say that there are regional differences, that is from above downwards there are differences in the ventilation received by the lung, that is the upper portion of the lung and the lower portion of the lung, they do not receive the same ventilation, and which part will receive the air first and which will receive later is also predetermined depending upon the elastic recoil forces and the volume at which the respiration is occurring. So coming to the volume we are talking about, that is the lung volume at which the respiration occurs, will determine how much ventilation and blood flow is occurring to different parts of the lung and the ratio. Now this is one thing which we can mention actually, that the ventilation to a particular region of the lung would also be in accordance with the units having normal compliance and resistance. If the resistance of the lung unit is different or the compliance is different, then as a result the total amount of ventilation received by it changes. That is given in terms of time constant. Time constant is a product of compliance and resistance, and it is equal to, by definition, where it is the time taken for 63% of the total ventilation to be received by a unit. So when 63% of the respiration, that is ventilation, has been received, it is 67%, 2/3 is received, then it is one time constant. So in a normal unit, respiratory unit, the one which is shown in the center, the time constant is 0.56 second. And the compliance is 0.8, which is considered to be normal. Here the resistance is 0.7. So the line in red shows the volume change occurring with inspiration. That is within 2 seconds, in less than 2 seconds, the maximum has been achieved. Within 2 seconds, or actually if you see it is slightly more than 1.2 or 1.3, the total ventilation or the volume has been achieved by that particular unit, and in 0.56 seconds it had received about 63% of the total amount of ventilation, whereas if those units who have got increased resistance will have increase in the time constant. If you see the curve in the green, it will take longer time for it to get filled, although it will fill, but it will fill slowly, and before it is completely filled, that is if we consider 2 seconds as the time of inspiration, before it is 100% completed, it will the next inspiration the next respiration step would come in, that is there is a change from inspiration to expiration and further changes occur. So in the third unit it is compliance decrease. So this is a unit which will not receive its full amount of air, but whatever it will receive, it will finish it in 0.28 seconds. So that is the time constant is less, but the total volume to be received or to be filled in this particular respiratory unit with decreased compliance is shown in the blue line. So the total ventilation would be affected by the slow alveoli, or the alveoli having higher resistance and the alveoli having lesser compliance, so that the total ventilation of the lung would be affected. This is just in brief in general. Now coming on to the next preliminary part, that is yeah, can you see that, all of you? Hello? Okay. So it will be a shorter topic because you are going to have a practical on the lung volume and capacities. So we have talked about that how with each inspiration certain volume of air is taken in, and with each expiration it is taken out, which is inhaled about 500 ml and called as tidal volume. So this is a diagram showing what are the changes occurring in the lung volume with inspiration and expiration, whether we take it in a normal quiet way or when we are doing it forced or taking maximal. So if you see the labels, the first one you have already known, the small waves, that is the tidal wave. The tidal volume is the volume of air which is taken in or out of the lung per breath, which is 500 ml. Then we have, if the person is asked, now what are the factors which determine the tidal volume? It would be dependent upon the neural command sending the message to the inspiratory muscles to bring about inspiration, and the elastic recoil forces of the lung and chest wall. Now in addition to it, the other arrows which are shown on the top, inspiratory reserve volume, I will just read it out for you so that it is familiar. At the end of the normal inspiration, at the point near 3000, the arrow is showing inspiratory reserve volume. So from here to top line is the inspiratory reserve volume, that is the volume of air over and above the normal tidal respiration, that is at the end of the normal inspiration. If you ask the subject to continue and inspire as much as possible, this reserve volume is the extra volume of air. Inspiratory capacity is the total, the tidal volume air which you had taken in, as well as inspiratory reserve volume. So, it is the inspiratory capacity is the sum of tidal volume and inspiratory reserve volume. It is shown in the right hand side of the diagram with the long wave going up. If you see below the 3000 line near 2000, we have the expiratory reserve volume written. That is the volume of air at the end of the normal expiration. If you ask the subject to expire as much as he can go up till a position which is called as the functional residual capacity. That point is the residual volume at the end. So, this functional residual capacity is the point at the end of normal expiration and includes residual volume. I think we will discuss this graph in the end, but how they are determined first, that because it will the similar diagram would be there towards the end. So, this is a simple spirometer. Spirometry is the technique by which you can measure the lung volumes and capacities. Volumes are the simple volumes that we have said, which cannot be further broken down, like tidal volume, inspiratory reserve volume, expiratory reserve volume, residual volume. Capacities is the sum of two or more volumes. So, whenever you can add these volumes, you can come to a nomenclature of capacity. We use this particular type of spirometer in our lab to show you how to measure the lung volumes and capacities. Here we have two cylinders, an inner one and an outer one blue. In between the two there is water which is filled in, that is forming a seal, that is called the water seal. In the inner cylinder we have a tubing coming from below, from which the person is respiring into the system. So, at the mouthpiece the person will take normal inspiration, expiration or the maximal one, and as a result the air is going into the inner one, and on the top is a floating drum which is shown, which is connected via a pulley. So, when the person breathes in and out, the belch or inverted drum moves up and down. If he expires, the drum will go up. If he inspires, it takes in, the bell will go down or the drum will go down. So, oxygen chamber, what is written, is filled with air or oxygen depending upon the condition. Normally we have it in air, because normally we are using air to inspire and expire. So, this pulley is connected to a writing mechanism on the other hand, which is shown here as recording drum. So, when the person inspires or expires, the pulley will move the system and there is a recording up and down with inspiration and expiration. This can be recorded on a moving drum. So, same thing which is shown here. The person on the right is connected by a water seal spirometer. Here we have a CO2 absorber also, so that CO2 does not rise in the system when he is breathing through it. And the pulley will connect to the pen, and then finally the recording comes like this, which is shown. Arrows are showing tidal volume, and on the left there is a y-axis showing the volume of air in liters. There is total lung capacity which is shown, which would be approximately in this particular diagram to be around 7 liters, because vital capacity has been shown up till there, and 0 is the functional residual capacity arrow which is shown below. Now, the maximum volumes what you can record from the spirometry are, whatever you can take in or take out can be recorded and measured by spirometry. What remains inside the lung cannot be measured. So, you cannot measure the residual volume. If you cannot measure the residual volume, then you cannot measure the functional residual capacity, which includes residual volume and expiratory reserve volume. So these cannot be measured by spirometry, and there are other methods to measure. So when you measure it, the spirometry you measure the lung volumes on the drum, and then you convert it to body temperature and pressure, because what you are getting the values are in the ambient temperature and pressure. You need to convert it into BTPS, saturated with water vapor pressure, and only after the correction then you should give the final values. So asking the subject to take a normal breath, at this point you ask the subject to take a deep breath. Take in, he takes up till top of the vital capacity. The dark arrow shows on the top where it can reach maximum, and then you ask him to expire as much as possible. So the curve moves down, and the lower point at around 1 is the lowest point where he cannot expire further. So if you see, can you see my face with the volume? Yes, can you? No. Okay, then I can't show. Otherwise I was thinking I will just show you that how you are asked. You ask this person to take a deep breath, and then you ask the person to expire as much as possible. So you need reach the lowest point of the arrow, and after that you ask him to continue the normal breaths. So this is just the normal procedure, and by this you can derive all the values which are shown in this diagram here. So the tidal volume is the volume of air which is entering or leaving the mouth per minute, per breath, sorry, and it will be determined by the mechanics of chest and lung, as we said, and by the neural drive from the respiratory control centers. If there is exercise, tidal volume will increase. If person lies down, it will decrease slightly, or it will increase. It will decrease because now the abdominal contents will force up the diaphragm. In pregnancy and obesity also, because the elastic recoil forces are also affected for the chest wall, the tidal volume decreases. Normally it is about 10 to 20% of the vital capacity being about 4 to 4.5 liters. But even if you are doing strenuous exercise, you cannot reach the normal vital capacity in routinely. That is, it may go up to 50 to 60%, but not more than that. So here again the same thing. On the left hand side, the first arrow from above downwards is the total lung capacity, that is the total amount of air from 6 to 0. It is the maximum, by definition, maximum amount of air a person can hold, the lungs can hold after a maximal inspiration, when he is starting from the lowest expiratory point. So when you are starting from the forced expiratory point and you take the maximal inspiration, the total is the vital capacity, and that including the residual volume, which you cannot measure, is called total lung capacity. So the three things now which we cannot measure with spirometry, I said whatever cannot be taken in or out cannot be measured. So residual volume, the volume remaining in the lung at the end of maximal expiration or forced expiration, it cannot be measured. Functional residual capacity, volume of air remaining at the end of the normal expiration. It will have the expiratory reserve volume, that is the volume which you can ask the subject ki aur expire karo, expire more, he will expire expiratory reserve volume. And it also includes residual volume. The third is total lung capacity, which again includes residual volume. It is from the zero position to the total lung capacity, maximum amount of air which a lung can hold at the end of maximal inspiration is called total lung capacity. So these three cannot be measured by spirometry, and we need to measure it by some other mechanism. What can be measured are inspiratory reserve volume, expiratory reserve volume, inspiratory capacity, tidal volume, and the vital capacity. The forced FCV or FVC? FVC is the forced vital capacity. This maneuver I have not told you yet, but shown here. Normally when you ask the person to take a maximal inspiration and expire, that is called as vital capacity only. You are not giving instructions to the person that do it as hard, as fast as possible. But when you tell the person at the point of maximal inspiration, I will tell you, take a deep inspiration and then you expire quickly, as fast as possible, as hard as possible, and as much as possible. So three instructions: as hard, as fast, as much as possible. So you are doing as fast and as hard. So when you are putting in more effort, it is called forced vital capacity. What is the idea of doing forced vital capacity when you are doing vital capacity? Why? Because by forced vital capacity, you would normally the two should be equal. The normal vital capacity and the forced vital capacity should be equal in a healthy individual. But sometimes when there is a disease process, the amount of air which can be expired is affected, and due to compression of the airways, and FVC decreases. So we will discuss from here in the next class. Thank you. And it will be an important topic, FVC maneuver and measuring the FEV1, that is the amount which can be expired. FVC maneuver is the maneuver done to find out how much is the volume expired in first second, and then we can find out whether the person has got obstructive defect or restrictive defect. The details of these will be worked out in the class, practical class tomorrow, but preliminary I will tell you tomorrow. So we will do little bit about the forced vital capacity maneuver and measuring FRC and the residual volume, followed by the next lecture, that is ventilation perfusion ratio. Thank you. So that we'll do tomorrow. That's all.